Hello everyone, and thank you for joining me today as we continue our conversation on related rates. What sets this apart from our recent lesson on related rates is in these related rates problems here, we're going to have to do a little bit of extra work on the side to find other values we are not explicitly given, and that's why the text is highlighted in red there. We may have to use some geometry skills, perhaps a little bit of trigonometry, to identify some value that we need that we were not explicitly given. And again, that's what sets this lesson apart from our last lesson on related rates. Now, in that last lesson, it was an introduction to these problems. We get ourselves organized by drawing a picture and identifying what we know and what we want, come up with some equation that relates to the variables we're working with here, differentiate both sides implicitly, then and only then substitute in what we know and perhaps do a little work to find something we don't know in order to get what we want. We've got three examples today. The first is a pretty typical AP Calculus style problem here in the form of a cone related rates problem. So water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 3 feet. All of that is represented in the diagram shown. How fast is the water level rising when the water is 6 feet deep? Diagram is already provided for us here, so let's get ourselves organized by writing down what we know and what we want. Well, what do we know here? In that first sentence, we said water runs into the tank at a rate of 9 cubic feet per minute, right? So like we've practiced, that's a rate, so I'm going to write down d something dt equals 9. Now, how about that something? Well, this is water running into the tank, and if that doesn't do it for you, look at the label here. This is cubic feet per minute. That's a rate of change in volume. Cubic feet would be volume. So dV dt equals 9 cubic feet per minute. What do we want? Well, the last sentence there in that paragraph says, how fast is the water level rising? And that's represented by h in our diagram, the height of the water. How fast is the water level rising when the height of that water is 6? That's what we want. So now we need to come up with some equation that has those variables in it. You know, V for volume, H for height, and when working with a cone here and working with volume, this one's maybe not too much of a stretch. And that isn't to say that you have this formula memorized per se. This would be provided for you. If you can commit it to memory, great, but the volume of a cone is 1/3 pi r squared h. This presents more of a challenge than our last lesson did because we've got a couple of variables over here. And so if I were to differentiate right now, I'd have to use the product rule. I'd get a dr dt in addition to a dh dt, and I'd be fine having dh dt, but having dr dt would be kind of a mess because I don't know anything about dr dt, and quite frankly, I don't want to know anything about dr dt. So here's that kind of extra added step. And if we were doing this in class, and I'm trying to keep this video brief, in class we would do a warm-up where we would practice this, but we can solve for r in terms of h in order to make a substitution here so that we have just h's in our volume equation. And here's how we do that. So coming over to our diagram, there's a couple of triangles here. I've got this one in red. I'll draw it again down here a little bit smaller. Okay, it's a right triangle where this distance is r and this distance is h. Okay, now kind of next to that, I'm outlining this triangle in blue, the bigger triangle here. That's a bigger right triangle where this distance here is 10 and this distance is 26, clearly not to scale, obviously. 26, where'd I get that number from? Yikes. 3 is that number there. Okay, perhaps better to scale. But here's the kicker about these two triangles. These two triangles are similar to each other. They both share this angle here. They both share the 90-degree angle that I drew in. And then the angles with the double arcs are also congruent because they are corresponding angles with these two parallel lines and the transversal coming through. So we do have 3 pairs of congruent angles making these two triangles similar. Clearly not congruent because the blue one's bigger, but they are similar. And what that means for us here is that there's a proportional relationship between the sides. If we compare corresponding measurements like r and 3 and also h and 10, those are like the matching measurements, right? The heights and the radii of the circular cross sections. That's a proportional relationship, so those ratios would be equal to each other. That's not the only way to set up that proportion, but that is a way to set it up. I can then solve for r in terms of h by multiplying the 3 to the other side, and now I have exactly what I want. I've got this expression that has r given in terms of h. And that allows me to come over here, make a substitution now. Volume equals 1/3 pi, and in place of r, I'm going to plug in 3h over 10. And now this equation just has h here. And that's going to make things easier when the differentiation comes around and then the substitution step. Now before I differentiate though, I'm definitely going to want to spend some time to clean this up, simplify it as much as possible. And to keep this video as brief as possible, I'm going to jump ahead a little bit. If you go ahead and you do some multiplying, some simplifying, etc., here's what you'll end up with after you clean things up there. 3 pi over 100 times h cubed. Switching colors now, we're at our differentiation step, dv dt. 3 pi over 100 is a constant, so we'll just leave that constant multiple in front, like we tend to do with constant multiples. We differentiate something cubed using the power rule, but now we're doing implicit differentiation here, and that along with the chain rule tells us to multiply by dh dt. Okay, and we can even clean this up a little bit here. Let's plug in what we know first. So switching colors one final time for the substitution step. We know that dv dt is 9, so we can plug that in. We are solving for dh dt at this instant when h is 6. And when I make those substitutions now, dh dt is the only unknown, which is good because that's what I'm trying to solve for. We'll have to do a little bit of algebra to solve for dh dt. I see that on the right hand side we've got a 3 times a 3, which would give us 9, which would effectively cancel like so, right? Giving me 1 equaling, what would this be? 6 squared is 36, so 36 pi over 100 times dh dt. And now I divide both sides by 36 pi over 100. And you can also simplify that fraction too. So I'm kind of doing a lot of stuff here without showing my work. But if you do simplify that fraction, we end up with 25 over 9 pi. Excuse me. In terms of a label here, that's the rate of change in the height. The height is measured in feet. That's the rate of change over time. Time is measured in minutes. So 25 over 9 pi feet per minute. If this were a calculator active problem, we could surely calculate that and round it to 3 decimal places, but this could very well be a no calculator problem. We didn't need a calculator at any point in this problem. The extra work here was going off to the side, setting up this proportion and using our geometry skills in order to solve for r in terms of h. That's pretty typical of a cone problem like this. Let's look at one more problem that has two parts, part A and part B. Okay, and again, the underlying theme here, besides just related rates, is that need to go off to the side, do some extra work, be it geometry work, trigonometry work, algebra work, whatever it is. So a 13-foot ladder leans up against a wall. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. The question says, find the rate at which the top of the ladder slides down the wall, because the base is being pulled out. Find the rate at which the top of the ladder slides down the wall when the base of the ladder is 5 feet from the wall. So in the diagram there, I've just labeled my parts. The height of the length of the ladder is not going to change here. It's a 13-foot ladder. It is what it is. So I can put that there for a constant. I've given the horizontal component here a name of x and the vertical component a name of y. So let's write down what we know. We know the base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So that's the rate of change in x over time, and that would be a positive 2. If that base is being pulled away from the wall, that distance x is getting bigger, it's increasing. What do we want here? We want the rate at which the top of the ladder slides down the wall, so we want the rate of change in that vertical distance over time, and we want that at the exact instant when the base of the ladder is 5 feet from the wall. So now we need some equation that relates these variables x and y, as those are the legs of a right triangle. Now this one maybe isn't as obvious when you're doing volume area problems with related rates, but when working with right triangles and working with the legs, one of my favorites is the Pythagorean theorem here. X squared plus y squared equals 13 squared. Let's go ahead and differentiate both sides implicitly. 2x dx dt plus 2y dy dt, and the derivative of a constant like 169 will be 0. And for what it's worth, we could just divide both sides by 2 to make this a little bit easier to work with. Now, when we go to plug in what we know, for x, we'll plug in 5. At the instant where we're talking about, x is 5. We know dx dt is 2. We're told that in the problem above. Trying to solve for dy dt, so that'll stay as an unknown. What I really don't know explicitly here is this value of y. We were never told exactly what y is equal to at this instant in time. So here's where we got to go do a little bit of extra work, and I'm going to do that in green over here. At the instant in question here, remember that ladder is 13, it is what it is. At this instant, this distance is supposed to be 5, so now let's go ahead and let's use the Pythagorean theorem to solve for y at this instant in time. And if you work with that and you end up solving using square roots, if you don't recognize this Pythagorean triple already, y will be equal to 12. So a little bit of extra work on the side there using the Pythagorean theorem. Trying to save a little bit of time here. A couple algebra steps to isolate dy dt. If you simplify the fraction you'll end up with negative 5/6. In terms of a label here, that distance y is measured in feet, time is measured in seconds here, so feet per second. If the fact that we got a negative answer here causes you to pause a little bit, think about that. It's always good to think about that. The top of the ladder is sliding down the wall here. This distance y is decreasing. And since that distance y is decreasing, we should get a negative rate of change here, negative 5/6 to be specific. Let's stick with the scenario and do one more problem, that's going to bring in actually a little bit of trigonometry here, which will be fun for us. So same situation, 13-foot ladder. Let's use the same names to stay consistent here. All right, we still know that dx dt is positive 2. That hasn't changed. Okay, but what we want has changed here. Okay, like the problem says, we want to know the rate at which the angle between the ladder and the wall changes when x is equal to 5. I'm going to use theta for that angle, but of course you could use any variable you want. So same instant in time here when x equals 5, but this time we want the rate of change of that angle. Well, there are a few ways you could do this. Some a little bit more involved than others perhaps, and that's what kind of fun about this. We don't have to do it exactly how I'm going to propose here, but this is the way that I think most calculus students would approach it. We need some equation that relates x and theta. Well, in a right triangle, all of our right triangle trig is in play here, like the Pythagorean theorem, but in terms of angles here, relative to that angle theta, x is the opposite side, and we know the hypotenuse is 13, so what we could do then is we could say that sine of theta equals opposite over hypotenuse, so x over 13. Would it be possible to use tangent as opposite over adjacent? Yes, but then you'll need the quotient rule perhaps, which makes it a little bit more involved. One student recently proposed using inverse sine, saying that inverse sine of x over 13 equals theta. Well, then you've got to know your derivative rule for inverse sine, which isn't the end of the world, but perhaps a little bit harder. So there are various ways you could do it. I'm going to stick with it this way right here. So we're ready to differentiate both sides, and our derivative rule for sine is cosine. Now I got to multiply by d theta dt. That's our implicit differentiation there. X over 13, think of that as 1 over 13 times x. So when we differentiate, we'll get 1 over 13 times dx dt. What do we know here? We know that dx dt is 2. We're told that. We're trying to solve for d theta dt, so that'll stay as an unknown. What about this cosine business over here? Yikes, we were never explicitly told what cosine of theta equals at this instant. Well, let's come over here and let's take a look at this instant in time. Let's take a snapshot here. Length of the ladder is still 13. Okay, we know this distance is 5 at this instant in time. On the previous part of the problem, we solved for this distance and got 12. So if we want to find cosine for this angle theta, cosine will be adjacent over hypotenuse. Adjacent over hypotenuse here will be 12 over 13. So bringing in some trigonometry there, which is always a good time. A couple algebra steps here to solve for d theta dt, and you will get 1/6. Time here is measured in seconds. What do we measure angles in this class? Well, we measure angles in radians, 1/6 of a radian per second. In our lesson today on related rates, one of the underlying themes was the necessity of doing some extra work to get some information we were not explicitly given. We saw Pythagorean theorem, we saw setting up a proportion using similar triangles, we saw a little bit of trigonometry there as well. That's it for us today on related rates. Thank you for watching.